Welcome back to dark mode. In this and the next video, I want to talk about the apply tactic. So we're going to go through a series of very serious, very important theorems to get a sense of how apply works. I'm just kidding. These theorems are they're total garbage. They're meant just to be exercises so we can see how apply works. Okay, we're going to work our way up. Ready? Here's the first one. Let's read it. If n equals m, and the list NO is equal to the list NP, then the list NO is equal to the list MP. Okay, think about it for a second. What would you do to justify this? If you knew these two things, why would you be able to conclude this thing? Well, my explanation would be, look, if n equals m, I can change that m into an n, and then this will turn into NO equals NP, but that's exactly that. Let's see if we can duplicate that reasoning in Coq. You could have given a different reason. You could have said, oh, well, if n equals m, I can turn this into NO equals MP, and then that'll be exact. Or because n equals m, I could turn this into NO equals NP, and then I could rewrite by this to change, I don't know, this into NP, and then I'd have NP equals NP. All three of those are great proofs. We're going to see how to do one of them right now. Okay, let n, m, o, and p be given such that these two equations hold. Here I'm calling them eq rather than h, just to mix it up. It's nighttime. We'll call it eq. We'll rewrite by equation 1 to change that m to an n. Let's just see it again. Catch it. The hand is faster than the eye. Okay. And now at this point, because eq2 matches our goal exactly, we can simply apply it. Now, the note here in the text points out that like, oh, well, you could have rewritten by eq2 and then use reflexivity, but apply eq is just shorter. Apply eq2 says, well, look, this is exactly what I needed, right? eq2 in our context matches exactly the goal, so simply apply it. Okay, the next bit is, I think, sort of the most important bit. Apply works with conditional hypotheses and can sort of automatically instantiate for all quantified variables in a very clever way. Let's take a look. So we actually already saw this happen a little bit, the conditional hypotheses, when I applied and intro. And I think I gave some sort of like stammering, inadequate explanation of what I was doing there. So sorry for that confusion. Let's make it really clear right now. So again, let's intro what we have and look at our proof state. Okay. We know by equation 1 that n equals m. Now equation 2, okay, the conclusion is indeed an equation, but eq2 is almost a misnomer, right? It's saying for any q and r that are a natural, if q is equal to r, then the list qo is equal to the list rp. Okay. Maybe you can see how this kind of generalizes what we saw here, right? That this is sort of an instance where both q and r are n. Now for us, we're interested in the instance where q is n, right? Then we'll get no, and r is m, and then we'll get mp. Now a neat thing about the apply tactic is that Coq will automatically instantiate for all quantified variables for you, and then it'll use conditional hypotheses correctly. What do I mean by that? Let's see. So if first here I've written down what the instantiation will be, incorrectly. Now I have it correctly. When I apply it, we see n equals m. So on the one hand, you might just immediately celebrate, thinking like, oh man, this is exactly what we needed. Eq1, we're home free. And you can see that from the tactic script I have on the left, right? That's true. But why is that what we got? Well, if you look at the instantiation here, once we instantiate it, it says you can get this conclusion if you can get this premise. So when I applied, any premises, any conditions on my conclusion became goals. So here we just had one, so we just have one subgoal. We'll see it again in the next proof. Let's do another example, a little more complicated this time, looking at how Coq will pick instantiations for the variables and do that same backwards reasoning that we saw. Okay. So nm are naturals. We know the pair nn is equal to the pair mm. Okay, so now we're just mixing it up. We've now seen equality at 3 different types, right? Here's equalities on pairs of natural numbers. Here's equalities on lists of natural numbers, and then we've seen a bunch of equalities on naturals themselves. That's interesting, right? EQB, the predicate, the function, only works on two naturals. But this EQ proposition seems to work on any type, and in fact, it really does work on any type. Okay, how does this proof go? Well, while it has a slightly different structure, here it was a bare equality, and now it's an equality between the tuples. It works just as well. When we apply EQ2, it says, oh well, this was the thing that you need to prove, right? It instantiated Q as N, R as M again, and it said, well, look, if the pair QQ equals the pair RR, then the list Q equals the list R. You wanted to prove the list N equals the list M. Okay, that means N is going to be Q, M is going to be R, but that means also that you need to prove the premise. Now, fortunately, we know the premise. EQ1 has our base covered. Great. Okay, one last remark, and then a tiny tactic that'll help us along. Okay, let's look at what we need to do. For any natural number n, if it's the case that true is equal to the result of running EQB on n and 5, now you might be wanting to read this hypothesis H as saying, if n is equal to 5. And at this point, we need to be very careful, right? This sign, this equal sign, like the equal sign of your childhood math classes, that is equality. That is like the mathematical equality. This is a function we wrote. And look, I believe, I hope you believe, that it coincides with this mathematical equality on naturals, right? That's what EQB works on. I hope you believe that. It's true. We're going to prove it later in the course, but we haven't proved it yet. And until we prove it, we have to be careful. And even after we prove it, we have to be careful. This equal sign is a proposition. It's a thing you either prove or can't prove, or prove doesn't hold. This is a function, and it's something you can run. It's code. It's computation. This is not computation. This is pure logic. That distinction may not make a ton of sense yet. We're going to, as the course goes on, start to draw this distinction between the things that run on the computer and then the things that we believe and prove, right, which are in this sort of purer mathematical world. Okay, if it's the case that our function for computing equality on naturals says that n and 5 are equal, it returns true, then it should be the case that running our same function on successor of n, okay, that's 2 plus n, all right, I'm liking the looks of this, just based on my own counting experience. That should be equal to 7, right? We'll judge it equal to 7 with our function. Okay, if we run simple, great. You might wonder why that happened. Why did the 7 turn into a 5? Well, if you look back at how EQB is defined, remember that it's this sort of nested double match, stripping a pair of successors off of both. So what simple is doing here is it sees this pair of s's, and it says, well, look, that means I can do 2 layers of recursion in EQB. So it'll take 2 successors off of each, and then it has to stop, because it gets to this n, and it says, well, I don't really know what to do with just the n, right? It could be a 0, it could be a successor of something, so I'll stop after taking 2 layers of successor off of both of these, which means that we'll be left with n, and just 5. Okay, so you run it, and you're feeling good, right? Look at that. Everything's coming up aces. And so then you say, great, I got this. And you just say, not today, cock. I'm not ready for this. What are you talking about? And you look at the error message, and it's hallucinatory. These two things are obviously the same, aren't they? Would that it were so. This says true is equal to EQBN5. This says EQBN5 is equal to true. Now, look, I agree that these mean the same thing, right, to you and to me. But to Cock, this is just different syntax. Cock looks at this and says, hey, true isn't exactly the same thing as EQBN5. EQBN5 isn't exactly the same thing as true. I don't know how to unify these. They don't look the same to me. Now, okay. All that means is you can't use apply directly. Now, some of you are like, reaching for rewrite and reflexivity, like just get me out of here. I got to be done with this. But I really prefer apply. Apply I find just sort of to be like a neater, cleaner tool. So at this point, what we could do is we could say symmetry, which is a tactic that says, hey, I have some equality. Could you just like swap it around? Or just like reflexivity invokes the principle of reflexivity. Two things that are obviously the same are equal. Symmetry says, look, if I wanted to prove EQBN5 equals true, I can just prove true equals equal EQBN5, right? I'll just work it out. And we actually don't need this simple because I did it earlier. It doesn't hurt though, right? Doesn't do anything. And now it matches H exactly. That's what I really wanted to have come across here. Apply only works when it matches more or less exactly. Now, Coq will run your program a little bit. Let's see why. Where'd we go? Thanks. Let's take a look back. So back here, if you wanted to, if you see your way through to the end, you could not simple before you did symmetry and be like, okay, and now simple and now apply, and that works. But you don't even need to simple. If you just apply H, Coq will run the program a bit and be like, it'll run it as far as it can, and if at any point along the way it agrees that they match up, it says, okay, we're good to go. I'm not going to do anything else. So there's a pair of paragraphs here, and normally I don't want to read every bit of text that's in the book, and in fact, the version of the file that I lecture out of is greatly abbreviated, but I want to go through this a little bit. So, okay, when can you say apply H? Okay, H has to be a hypothesis in the context or a previously proven lemma. Either way, it has to have this shape. For some number of for-alls, and then a chain of hypotheses, and then a conclusion Hn. The current goal should have the same shape as Hn for some instantiation of each of the variables, right? We saw that up here, right? So like, because this was a pair of like an equality between these two singleton lists, it matched up exactly and it was able to sort of instantiate things to match up. After running it, you're gonna have a sub goal for each H1 through Hn minus 1. Now, if there's no H1, if H is just like for all X, blah, you're just gonna be done. All right, and then this paragraph talks about the informal analog of it that I'm going to leave on the side. All right, but I recommend read this again, see if you can match it up to your experience of what each of these applies here did. In the next video, I'm going to talk a little bit more about apply, a special form of the apply tactic called apply with, and then we'll be able to sort of wrap up the day. I know this is more video than usual. We're introducing a lot of new stuff. I'm hopeful that I'll get away with less watching time. In any case, I've also tried to dial the homework back so that the increased watching time is balanced by slightly decreased programming time. In fact, your programming will all be proving, so it'll all be actually quite different from what you've seen so far. Okay, see you soon.